Greetings, everyone. This is TANMAY KUSHWAHA, third year undergraduate IT. And this is my project, adaptive ML-based video compression using segment-wise CRF prediction. Okay, so what was the motivation of my motivation behind this project? Okay, so modern video compression uses static compression parameters that fail to adapt complexity. This presentation introduces an intelligent machine learning driven approach to optimize compression parameters per segment, maintaining consistent perceptual quality while minimizing wasted bitrate. Okay. So what was the core problem that I tried to solve through this project? Okay. So a single constant rate factor cannot effectively handle the errors we depend. So when you're compressing a video and you have a particular value of compression parameter is fixed, the video is bound to be compressed in the same way, which should be varied depending on how pacing the video has, how much motion the video has, how much lighting the video has, how much static scenes are there, how much fast-paced scenes are there. And one size fits all approach creates quality and inconsistency. Okay. So our goal was to use machine learning to predict optimal CRF value per segment, maintaining target perceptual quality while minimizing bitrate waste and encoding attempts. So these are the objectives of project. First, to predict optimal parameters, then maintain target quality. So we have this option where you can choose a quality, like you can choose a VMAF value. We will tell you what this value stands for in the later slides. So you can choose this value, and according to this target value, the video will be compressed. What other objectives did we have to build a data set? Like we had 4K videos. Now, through that videos, we wanted to make a data set. That data set consists of the video features, like entropy, spatial features, and different sort of quality parameters like VMF. And the last part was to deploy this ML pipeline. So we will discuss all these in the slides. So let's first start with knowing what these parameters are. We are trying to adjust the CRF value, which is for controlling value balancing bitrate and quality. Okay, lower CRF means high quality and large size files, and higher CRF means smaller files but more compression artifacts. Okay, so higher the CRF, lower the lower the size of the file, the more the compression. Lower the CRF, higher the quality of the file, larger the size of the file. Now let's get to VMAF score. So what is a VMAF score? Netflix developed a perceptual quality metric combined PSNR, SSIM, detail loss and motion analysis into a unified 0 to 100 score. Higher VMAF indicates better perceived quality. So PSNR and SSIM are also indications of video quality. Uh, Mixing them together and also adding detail loss and motion losses, there's a score given to it, which is a VMFF score. This can be taken as a quality metric. Here we have used only this as a quality metric. So in the study database, we have the values of PSNR and SSI. Okay. So what thing is there's non-linearity between CRF value and MPF value. There's not a linear relationship between them. The relationship between the content complexity, okay, and optimal CRF is non-linear and highly content dependent, okay, requiring ML module to get the values of the parameters for effective compression. So here we meet two models. First predicts the VMAF value. So suppose we have the CRF value and we have the content features. We'll discuss what the content features were in the later slides. Okay, so let's see. There was like entropy, spatial awareness, and motion. So we give content features and CRF values input. Output is predicted VMAF score. This model learns perceptual response to input settings. Okay. So this model takes CRF value, like we know how much compression do we have to make. Okay. And this predicts the quality that the after compression, what the video quality will be. And the second model we trained is we want the quality. We want this quality. And this predicts what is the optimal CRF that we need to get at least this much VMF. Okay. And this also takes content features as input along with the VMF value and gives optimal CRF value. Reverse maps quality target to compression parameters. Okay. So let's see about the first model. The input features the spatial variance, which is the texture complexity, entropy, which is the randomness in the information content, uh, motion estimates, resolution dimension, and CRF value. These are the input features. Model architecture. We are using regression based approach. We use random forest technique to capture complex interactions, and we trained multiple encodings per segment at varied CRF value, create rich VMAF CRF curve for model learning. So what we did was we had this raw video in YUV format, which is a raw format. Okay, there's no encoding in that. We encoded that raw. We first segmented that into various clips of small duration, and each clip was encoded using different CRF values. Um, And in response to CRF values, we get the VMF values. Now, we train this model to take CRF value and the other input features and give VMF value. We train random walks. On the right, you can see here, uh, we have this segment, which segment name, CRF value, PSNR and SSIN value, the spatial variance, the motion, the VMF value, and the entropy, and the resolution data. So the model had uh, R square score of 0.987 and RMSE, which is um, mean absolute error of 2.015. Okay, so yeah, what we did next was we do a pseudo dataset simulation. Okay. So we first had, like I told you, here in this, we had given some CRF values and some VMAF values predicted. But uh, as much, oh, like you want multiple CRF values to be trained for a model that predicts CRF values. So the way under trained, the bit will not perform better. It will perform poorly. So to uh, get these values, you might need to encode them again and again, which takes a lot of time. So what we did instead is, instead of doing encoding again, first we trained a model that predicts a VMF value. Now we simulate these CRF and VMA values. So, like to create this pseudo data set, we input some CRF values called what VMA values it might have. And input features we already have by the videos, so we can use them. And now we created a pseudo data set that has multiple values of CRF. Here we had only three values. So now we use this data set for training the other model. Okay, so the other model is optimal CRF prediction. So in this model, you have input features like spatial variance, motion intensity, entropy, resolution, and target EMF. The purpose of this model is to model complex non-linear relationships between video characteristics and optimal compression levels, trained on pseudo dataset to generalize across diverse content types. Okay. So the model had a mean absolute error of 0.454 and R-square score of 0.94. Okay. The model demonstrated robust generalization across diverse content with prediction errors under 0.454 CRF units and high correlation coefficients validating the approach. Okay. Uh, this was our pipeline. So, see, we had a model. So, How this will take place is first you have a video, you segment it into different chunks. Say 2 seconds, say 1 second to say a low value. Like in the streaming platforms, it's like some frames are transferred at once, like this, or even frame wise. You can do the stream wise as well. But the VMA value somewhat depends on the neighboring frames as well. So let's say chunks you have. So you have a video, you divide it into chunks, or when you are streaming a video, the video is sending in chunks, right? So that chunk videos that the features are extracted of the segments, then uh, based on the CRF prediction, the videos, the segment of the videos are encoded. There's adaptive encoding using FFmpeg. Adaptive encoding means for different segments based on the features like we talked about CRF prediction depends on spatial variance, motion intensity, entropy, resolution, and target. Okay. So target might be constant for all the frames, but the resolution, the entropy, the motion intensity, and the spatial variance may change according to the frames. And this is where this approach plays into. Um, so depending on the features, the CRF value might be protected. And this CRF value can be used for anything. This is what protein coding is. And finally, the output is given. And at the output stage, you can use the encoded signals and evaluate fine bitrate and VMA results. Okay, so system implementation was first feature extraction, then model training, CRF prediction, then dynamic FFPG encoding. That was our implementation. Okay. So uh, let's talk about the feature abstractions. We talked about the various features we trained the models from. So the features were spatial variance, which measures localized texture complexity and structural detail within a. Then there's entropy, which quantifies the information richness and randomness of pixel values, indicating visual details. Then there's motion, which estimates using frame differencing to capture temporal complexity and scene changes. And we have resolution. The frame size is included as a fundamental characteristic to the content. Okay. So for every segment that we had for training it, we uh, took we started these features through OpenCV and yeah, used it. Okay. This is the variable correlation analysis. So you can see how VMF and CRF varies through these curves. Okay. And here below, you can see how the other parameters vary among themselves. Like you can see over here. Uh, yeah, this is an inverse model performance like the model we trained earlier to predict the CRF values or the predicted values and different values are plotted. Let's have this performance model. And here you have parapoid scatter and regression links. So here you can see this is the VMF value and this is the spatial variance I can zoom over it. There's the motion, entropy, resolution, CRF value, and VMF values. How these depend on each other. This is the analysis of the polygons. And this is the coefficient correlation curve. So you can see the VMF value depends a bit on spatial variance, little to no on motion, then entropy. Then since we had uh, resolution as fixed for the data set, there's no variation over here. See that. CRF value and the values have a have somewhat direct correlation. So we can see that from the graph. Okay, we also had this to show how they vary from how they how the variation is there. Okay, how the correlation is there. You can see it from this graph. CRF value and the VMF value with these two graphs as well. Okay, so yeah, CRF values depend a bit on entropy motion and species awareness, but majorly on VMF. Let's move to the other side. So, as I told you earlier, how we trained for the data set. First, we split raw IO videos into smaller clips and processing. Then, multi-CRF encoding. We encoded each segment across a broad range of CRF values, say 15 to 40 using FFFG. Then VMAF computation accurately calculated the VMS score for every encoded segment against its original reference. Then comes data set creation. We formulated a comprehensive data comprising of features, CRF values, which gave VMAF views from the process segments. Okay. Then there's training of VMF parameter. So we developed and trained only one. We talked about model one and model two. Okay. So the model one, we trained it to precisely predict VMF scores based on the content features in CRF. Okay. Now what we did is we did CRF simulation. So we traced model one, simulated and identified optimal CRF value for desired targets, VMF levels, right? And trained model to generate optimal CRF data to infer the best CRF from content features at target VMF value. So this is the complete thing what we did. Okay. A major part of the project was data set creation only. So the model was uh, random forest, so it was easy, but main thing of the project was data. So data created. Okay. So we talked earlier about segment-wise adapting video. So the raw video is split into different duration segments, ready for analysis. Okay. So we extract and predict. We features are extracted from each segment, and the ML body predicts its optimal CRF value. Each segment is then encoded independently, okay, using FFmpeg with its unique predictive CRF, and we log and concatenate. Okay, the CRF predictions and the output that is logged, and all encoded segments are seamlessly merged into the file. So here the performance um, you can see for different frames. Okay, so like say we had a video of only two segments. Okay, we'll just show this quickly. Okay, we have a video of two segments. First was around same as the second one, but it differs because of its it features. Okay, so here the CRF value is 23.95 and here the CRF value is 24.0. We uh, we took a constant target VMFA score of 80, but we got even better 97.5. Okay, so there was a major but it's a positive, so we can like that. It's better that you have got better results. And surprisingly, the mean compression ratio was 0.05. So the file, which was earlier 1.16 GB, was converted into a file of 16 MB. So this was something that this method did. Okay. Now it's the evaluation pipeline. So to rigorously assess the effectiveness of adaptive encoding system, we employed a comprehensive evaluation pipeline focusing on key quality and effective measures. The approach involved comparing adaptive encoding performance and clinical fixed information. Okay. So we achieve a mean VMAF score. We calculated the mean absolute error, and we also calculated the file size reduction. Okay, so let's see. Yeah. So this was the quantitative performance results. Uh, as we showed you earlier, the mean VMAF score was 97.5, which is good. Even though we target for 80, we got 97.5, which is 1.5 greater than what we needed. And the compression ratio was 0.014. So 1.1 GB of file was converted to 16 MB of file. Okay. So our adaptive ML based video compression system demonstrate highly significant improvements across screen matrices when compared to traditional fixed CRF encoding approach. Here we had a CRF encoding approach. So this I didn't show you in data, but this video was of about 710 MB. Okay, then CRF value was of about 10 to 15. And here we can see a adaptive CRS encoding. And this was surprisingly of very less point compared to that. There's a lot of 30, 26 to 30 MB. Okay, and you can see the video quality is around the same. You can see sharper textures, you can see less blocking, high motion areas show, like we can't see the video in the slides, okay, but high motion areas show significantly fewer compression artifacts. Uh, there were sharper textures that are encoding preserves finer details in textures. So depending on the frame we are doing the compression. So eventually the video features that were neglected earlier, but considered for compression. And so we had a better video output, right? And they were consistent quality, like overall brightness and constant have maintained more uniformity. Uh, skip to this. The adaptive CRFs both successfully achieved comparable slightly improved perceptual quality while drastically reducing the mean error from the target. Okay. And yielding substantial 50% size. Oh, okay. We had much um, size reduction. Okay. So, what is the key observation that we have? Consistent perceptual quality. So, the adaptive system consistently maintained uniform perceptual quality across diverse video content and ensured high quality video experience. Also, our ML model demonstrated strong generalization capabilities, accurately predicting near optimal CRF values, even for previously unseen video streams and content types. Okay. So there was actionable feature insights like high motion in a segment typically correlates with a lower CRF, and low entropy allows to higher CRF without significant quality loss. And also we had optimized efficiency with trade-off. Okay. So while achieving significant compression benefits, there's a slight compute overhead introduced by the segment-based re-encoding process. So this is the trade-off it had to face. Right. And so we also had an overview. We should. So let's move to the conclusion for future scopes. So till now we demonstrated how we can encode it segment-wise, do adaptive encoding, and get a very good size reduction. But what we could have shown you, or what we can do in future is, we have two devices trying to say, one trying to stream to the other, and this compression and this encoding happens in real time. So this is what we can do in the future works. Also, this ML model can be used in uh, embedded devices or edge devices for saving the memory when recording videos. Like, say you had some recording cam or some these some of this, and it can then uh, dynamically change the parameters to get optimal file sizes. And even if you had to stream this, like say the camera is not running, you want to stream to your device, the camera in the onboard computer has this ML model running, and from that onboard camera to your system, the file transfer will be easy since the data file is reduced and the bit rate would be drastically more uh, had a more efficient file rate. So this is what we can do. What are key conclusions? We successfully implemented ML-driven per segment video compression. We demonstrated significant bitrate savings while preserving consistent perception quality. We validated the feasibility of integrating machine learning models with FMPG for dynamic control, and we achieved a 15% size reduction with comparable or improved quality. So what are the future expansions and roadmaps? Sorry, when I told you earlier, the other would be deep optical flow. Okay, replace the handcrafted motion features, so we just add differences between the pixels and try to carve in motion. We could introduce optical flow. Then there are CNN-based predictor. So we could integrate a CNN-based specific quality predictor for more precise VMF estimation. Then there's a real-time adaptation. We could develop real-time adaptive encoding capabilities stable for live stream application. That is what I told you. And we could have multi-resolution model. We could extend the adaptive encoding model to support optimal compression for higher resolution 4K or 8K. So this was it from my side. Uh, Thank you, and have a very, very nice day. Thank you.